Okay, so now in this lecture, we are going to discuss oxymercuration reactions with alkenes. And this is a bridge mechanism. So because mercury 2 is a large atom with at least one lone pair, it is going to form a bridge intermediate, similar to large halogens like iodide and bromide that we saw in the last video. In other words, mercury is still in category B in terms of how we grouped our electrophiles early on. So the mercury is bound to two counterions or acetates. And that mercury is therefore electrophilic, and the oxygens are electron withdrawing groups. So mercury can be attacked by the alkene. Mercury has a lone pair that can then form the second bond of the bridge, and one of the acetate groups is going to then serve as a leaving group. And this will take us to two intermediates. One where mercury could form a bridge from the top face of the pi system, cis to the methyl group, and that would push the other methyl group back as it rehybridizes to sp3, and the mercury now has 3 bonds or is sharing an extra pair of electrons, so it's positively charged, just like all other bridge intermediates we saw were containing a positive charge and therefore are electrophilic. Because the alkene is planar, you can also have addition of mercury from the back face, which would push the methyl group forward. And the other methyl over here remains on the front face, as that carbon does not undergo reaction. So the eventual nucleophile in oxymercuration is going to be some oxygen molecule in the solvent. So oxygen containing molecule, that could be water in this case, or alcohols in other examples. And because that oxygen is nucleophilic in water and the water is abundant, it is going to attack the bridge. And the water is going to attack the carbon of the bridge that is more electrophilic. Just like any other bridge intermediate, there's more positive charge at this tertiary carbon than there is at the secondary carbon. So water is going to attack and break the bridge, or give a lone pair back to mercury. And that's going to give you an intermediate where mercury remains on the secondary carbon on the front face of the ring. The methyl group is fixed, and the water must attack trans to mercury, or it must open the bridge from the opposite face. Just like any other bridge mechanism, this is an anti-addition, where that methyl group at the tertiary carbon gets pushed forward. And you get stereochemical inversion there. So the same mechanism for the other diastereomer of the intermediate is water attacks that tertiary carbon and gives you a lone pair back to neutralize mercury, where mercury was in a bridge on the back, and therefore water will attack from the front. Pushing the methyl group down. Okay, so we have another intermediate here, but we can already see where the regioselectivity comes from. So the oxygen is bound to this more substituted carbon. So oxymercuration is a method of adding an oxygen atom, either an oxygen that will become an alcohol or an ether, in a because the bridge intermediate has more electrophilic character at that more substituted carbon. So the oxygen ends up being bound at the more substituted carbon. So the final mechanistic step to get a neutral product after reaction 1 is to use a base in solution, such as another water, or you could use an acetate, and that water is going to deprotonate the acidic proton to give a lone pair back to the electrophilic oxygen. That's going to produce 2 products. Where you have this mercury alcohol. Or mercurinic alcohol. And the relationship here between the products is diastereomeric. If you were to do R&S, you would find that you have the S, S, and S compound, and here we have switched both stereocenters to R, but the other remains S, or you have a fixed chiral center that was S in the beginning and did not undergo any change. And so the relationship, as I mentioned, you have a pair of chiral diastereomers. And if you just have step 1 here of mercury and solvent, then you're going to simply get those anti-addition products only, where you make the SS from this Z alkene or the RR. However, oftentimes we are not interested in having mercury in our final organic product, and we will go on to do a second step of reduction to remove that mercury. So let me show you the reduction step. And I'll just resketch these 2 diastereomers below, where OH and mercury are trans in both products. So now if you take these and you subject them to sodium borohydride, which is a reducing agent, and you do not need to know the mechanism for sodium borohydride with mercury, but it basically acts as a source of H-. It's like a nucleophilic hydrogen. That hydrogen magically replaces mercury via a reduction reaction at carbon. And this carbon here had 1 hydrogen in the initial product, but now it has 2. So I'm simply going to draw dimensions only at the stereocenters. Okay, so this carbon now has 2 hydrogens on it, one of which came from the hydride source. And there are no chiral centers in these products because there is now a plane of symmetry that goes through the carbons that were previously chiral. So there are no asymmetric centers because those stereocenters lie along, right, the plane of symmetry. However, these are going to be different compounds. In one compound, we have the methyls on the same face of the ring, cis. In the other compound, the methyl groups are trans. And cis-trans isomers are diastereomers, but because these do not have any asymmetric centers for which we can assign R and S, these are simply achiral diastereomers in this example. So you do make 2 diastereomeric products, they're just not chiral. Both cis and trans, because the mercury bridge could have formed from the top or the bottom face of that initial carbon-carbon double bond, planar sp2 carbons of the alkene. So this is a bridge intermediate, and after step 1, with mercury and water, or mercury and a solvent, you're going to get that anti-addition only, where mercury and oxygen are trans. But after you reduce off mercury with this reducing agent, sodium borohydride, it is going to completely erase any memory of where mercury was on product. And therefore, we lose that anti-stereospecificity, or the second step is not stereospecific. Although the first step was an anti-addition. So let's examine one more example where we use mercury with an alkene where there's a pendant alcohol in the structure. And we know that the alkene is going to be nucleophilic and attack mercury acetate. Mercury is bound to two electronegative oxygens and therefore is electron poor, but has a lone pair. So the pi bond is going to attack mercury, kick out a leaving group, and mercury can make a bond with what was the alkene to form a bridge intermediate. I'm not going to show any stereochemistry for the bridge intermediate, and you'll see why in just a minute, although it could form on either face of the alkene. So now we have THF, which is a inert ether solvent. That's THF. There is no water in this solution, but there is another oxygen nucleophile, an alcohol. And the oxygen nucleophile can attack the bridge in a very fast intramolecular manner. Remember that the tertiary carbon of the bridge has more electrophilic character than the primary carbon. So the oxygen nucleophile will quickly attack that tertiary carbon to deliver a lone pair back to the electrophilic mercury. And this is a fast reaction because it is intramolecular and forms a 1, 2, 3, 4, 5, 6-membered ring. And we know that 6-membered rings are stable. And therefore the transition state is stable. And therefore it's going to be a fast reaction. So the oxygen will be one of the 6 members in the ring and will bear a positive charge after attack. And the lone pair from oxygen is forming a new sigma bond to a carbon, that is carbon labeled number 6, which has a methyl group. It has another bond to mercury. So this carbon here, number 7, is the first one outside of the ring. Number 6 is here. If you go around the ring and count, you'll find 5, 4, 3, 2, and oxygen was 1. So the final step is going to be to neutralize this ether product by deprotonating or giving a lone pair back to the electrophilic oxygen. You could do this with any base in solution. You could use the solvent or you can use acetate. Acetate will deprotonate here and give a lone pair back to oxygen. So we get this ether now, mercurinic ether, which once again, you could leave that product if you just had step 1, but if you have step 2 of sodium borohydride, that will add a hydrogen to the carbon that is bound to mercury. And it's going to give you this product. So this carbon here had 2 hydrogens, and now it has 3, or now it's a methyl group. So this time we get an ether because we started with an alcohol nucleophile. Whereas in the last example, we started with a water nucleophile, and that made an alcohol product. Okay, so you can use either alcohol or water nucleophile with a mercurinium ion or a mercury bridge and successfully make a new oxygen-containing substrate or a new oxygen-carbon bond in your product. So you also will notice that I have one chiral center that we need to append to these intermediates. This chiral center at carbon 2 had the S configuration, and that carbon 2 did not undergo reaction. So to maintain that as S, I actually have to make that methyl group a dash on carbon 2 here. So there it will have the S configuration. And that stays the same throughout. So we start with one chiral center that had this S configuration throughout, and we did not make any new chiral centers. Okay. So what that means is that you get a single enantiomer product this time, a single chiral molecule. Since you started with a single enantiomer of starting material and you did not generate any new stereocenters. Okay, so that's all I have to say about oxymercuration. We will do a similar reaction with alkynes in the next chapter, but for now you can find practice with this in my Orgo 1 course guide at chemguides.com.